empty now, so we're gonna start. So hi everyone, it's a pleasure to see you on this third Sunday morning. So today we're here for your very last workshop. So it is my pleasure to present what's going to happen today. So we're at week 8. We're going to talk today about model generalizability. So there will be both very new exciting stuff as well as general stuff that you can use in your everyday machine learning journey. So our instructor for today would be Dr. Laya Rafiee. So I'm going to introduce her later. So just as a reminder, we are here. This is the very last week of McHag 2023. We're going to have a closing ceremony as well, but this is your last workshop. Of course, you will have the tutorial next week, and also you know that you will still be able to access all the resources, the recordings, and notebooks. So make good use of them. Of course, like the best way to learn is to attend the live workshops and to attend the tutorial to ask your questions, but you already know that. But you still have access after to resources. So now we are here for the model generalizability workshop with Dr. Laya Rafiee. We have two amazing mentors, some returning and some new. I think Eugene already introduced them yesterday, but I've seen that Nguy is here today. So feel free to ask questions on the chat, and either she can respond to your question, or Dr. Laya Rafiee will be pleased to answer them. So now it's my very own pleasure to introduce Dr. Laya Rafiee. She has completed her bachelor and her software engineering and her master in computer science in Iran at the University of Sahid Beheshti University. She did a PhD of computer science with the main focus on anomaly detection and out of distributions and domain adaptation. And now she's a postdoctoral fellow at our very own Angle Lab at McGill University. She's working on developing an AI-based triage model for colonoscopy referrals. And she's also working in segmentation of colonoscopy videos. So she has great expertise to deliver this workshop today. So thank you very much, Dr. Rafiee, for your time and for your presence today. And now it's my pleasure to let you start your work and share your screen.
Thank you so much. Hello, everyone. It's my pleasure to be here, and thanks for inviting me. I'll try to share the screen. Let me know if it works.
Yeah, we can see your screen. That's perfect.
Okay, that's good. So good morning, everyone. Or actually, I should say, like, depending whatever time zone you are in, I hope you all have a good time. And I hope that this workshop will be useful for you and we all learn new things today. So today, I would like to talk about the generalizability in deep learning and machine learning, and some of the pitfalls, and what are the best practices, and how we can improve the performance of the models and improve the generalizability. So, so I would like to first introduce you what is actually generalizability, give you some definition, then I would like to give you some example about AI model failure with respect to generalizability to show you why this topic is important. And we'll review some of the malpractices that's been done by us that hurts the generalizability of these models in general machine learning and deep learning. What are the solutions? We're going to review some of the solutions that we have for some of these practices that we made wrong. And then we're going to see a few coding examples. So, so generalizability in a nutshell. So assume that we develop a model in a lab. Everything is working pretty well. Like all the performance metric that we calculate shows that the model is working well. We send the model to one of our friends somewhere else to try on their test data set, and they realize that it's not working as we saw during the lab. So it seems that the model is not performing, like it's not having the best generalizability. So what we're looking for, we want to have whatever we develop here in the lab, we wanted to be able to perform as well in the real world. So in this way, we can say the model is generalizable to new example, to unseen example. So this is like an abstract, like a definition of generalizability. But I also put like other definition that I would like to review. Probably some of them you already know, or maybe all of them, but I wanted to review them because these are important for this workshop. The first thing is that, like you already heard about machine learning, the biggest machine learning assumption, IADs, independent and identically distributed data. So the thing is, this is very important because many of the machine learning models and the loss functions and models like this are actually built up on this assumption. And the other thing that I found probably is very important to know when you are talking about model generalizability is the inductive bias. So inductive bias is actually specific to the model's assumption about its data. And sometimes it can lead to like underfitting. So I will give you like a few examples. Assume that we want to have like we have like 10 classes of different birds and we want to do classification for them. We cannot use a regression model for this because these are very different. Like the assumption of the regressor is different from what we have as a data. Or in another example, like for those 10 classes, we cannot use a binary classification model because the assumption of those models is that the data is including two sets and like they have to distinguish between these two. So although these seems to be very easy to mine, but I wanted to just give you the idea about how important inductive bias can be, because in some cases, you might encounter situations that the model that you're using seems to be very perfect for the like data set that you have, but the performance that you're getting is not as best. And you have to go back and see what are the assumptions that the model makes, and maybe you have to refine everything. So now these two, like there are other definitions that we need, but these two are more important here in the context of generalizability. Also like to review a little bit about different errors that we have. I'm going to do it later. So I would like to also give you like a sense about the situation that low generalizability can happen. Take this as an example. We want to have a classification model for different dogs breed. And for the training, we provide like several samples for each classes, high resolution images of the dogs, and we train our AI model. Seems to be working perfectly. What we would like to see during the test time, we would like to see example from similar classes that we used to see during the training. But it's not always the case. We might see example of samples that's not actually belong to any of those classes. We might see like images of the cats, or we might see, be in a situation where like the quality of the images that we see during the test is different from what we saw during the training, like low resolution images, blurry images, or instead of like a full dog, we might have like part of the dog. This is the real scenarios that usually happen when we develop an AI model. And we have to be careful about this because these are the places that low generalizability actually happens, and they're very common. So now I want to define the different types of errors. So you already know a bunch of those errors, but you might not know some of them. So I decided to have a quick recap on this. So the training error is the error that's made by the model on the training set. And we usually use this in order to learn the parameters of the model. For the validation set, the error that makes by the model on the validation set. And we usually use this validation set and the error on the validation set as a way to tune our hyperparameters and find the best hyperparameters for the model. There is a test error. That's the error that makes by the model on the test set. So about the test set, we usually want to provide a test set that resemble the real world distribution of that particular task that we're doing. But the thing is, this is not always possible, and sometimes it's very naive or over optimistic about us. So I'll give you an example in medical. Assume that we are a team and we want to build an AI model to detect some particular disease in a state in US. We gather the data from that particular state in the US, but the thing is, there's some feature about that particular disease that only is specific to other people who are living outside the state. So since we don't gather those data, and since we don't have those data fully, so the distribution of the test set is not a real world distribution. It's not replicating that. It tries to be close, but it's not. So this is something that we have to know about the test set, because this is going to impact the generalizability. The generalization error is the error made by the model or unseen example. Since, as I said, we cannot provide all different examples in the real world for that each particular task. So we usually use the test error as a proxy for the generalization error. So another type of error is known as Bayes error. Bayes error is something that it is intrinsic to the task or data set, and it is independent from the model that you're using. Like whatever model you're using, the best model that you think, this Bayes error is not related to the model. It's independent from that. And it's not something that we usually can calculate. It's a theoretical term. And I'll give you an example on this Bayes error, again, in the medical context. Assume that we want to predict the chance of getting cancer for different patients that we have. The information that we have to build these kinds of model, we have blood test result, we have CT images and stuff like this. But we also know that one particular factor for defining what are the chances of getting cancer for a person is the genetic information. And we don't have that genetic information here in these data sets or these tasks. So because of this fact that we don't have all the information defining probability of getting cancer, we can say that we cannot achieve the lowest error possible. The lowest error possible is where we have all the information. And since we don't have it, this is the lowest, the Bayes error is the lowest that we can achieve, and it's not near to the thing that we want. So now we know about these types of errors and what are the errors that we have to rely on when we are reporting the performance of the model. And now I would like to draw your attention about cases then these AI model actually failed, because I wanted to show you how important the generalizability can be. This is actually, I can tell this is actually the most important thing that we want to do when we want to develop an AI model. We want it to be not only working on the the validation set, performing well on the validation set that you have. We want it to work best on the test set that we didn't see. So before I give you the example, I would like you to draw your attention to some reason that might cause failure of these models. There might be different reasons, but I would like to emphasize on two most important reasons. The first one is known as data selection bias. This feature can cause AI models have a lower performance when they encounter to like specific race or ethnicities and so on. I will give you an example. Like a few years ago, like an AI model that was developed for detecting breast cancer. It in the literature and on the paper, it seems to be working very well. Like the performance seems to be quite good, but in the practice and in the clinic, when they used it, it didn't perform as well as it promised. And unfortunately, it was working really well on white women, but it wasn't working that well on Black women. So researchers went back and studied why this happens, and they realized that the data sets actually, like more than 80% of the data set includes like information about like white women, and less than 8% were from like Black women, and the rest was other minorities. That's why the model could not perform that well. So in this case, during the data gathering, we kind of impose the bias inside the model and force the model to perform better for some specific majorities. And this is something that we have to be careful about. Sometimes it's inevitable. We cannot gather more data. We cannot provide like for better distribution of the data close to real world. But this is something that we have to be careful about, especially in the medical when you're like reporting something. Another thing is known as shortcut learning, or sometimes, or we refer to it as learning spurious feature. What I mean by shortcuts is that in the context of like deep learning, or in particular in like neural networks, they tend to learn easy pattern in order to do the prediction. And we know neural network to be lazy. And this is something that can hurt generalizability of the model if they don't pick up the right features. I will give you like two examples, one in the context of medical and another one in non-medical situation. During COVID-19, around like 2020, there were a big interest between researchers to develop AI models to detect COVID-19 positive cases and speed up the detection process in the hospital. Many papers has been published, but unfortunately, they didn't work as they promised in the literature in the hospital. When the people wanted to use them in a hospital, there was a big failure, and they didn't perform as well. So researchers were studying like why this happens and wanted to see what's the issue for these models, because like, as I said, almost all of those models failed to be helpful during the COVID time. So like there were some studies, but in one of the studies, researchers tried to look into the prediction of these models, and they looked into the data set that these models were trained on, the saliency map, and they realized that when the model wants to predict by looking at the saliency map, they realized that they were relying on some feature outside the long area. Some of these features were like markers or annotation or something that were there by mistake, but the model used those to do the prediction. I will give you I will give you an example. So take this as an example. In this scenario, they studied one of the data sets that many researchers actually tried to use that public data set in order to build an AI model. They realized in many of the positive cases, there were some feature in it that they weren't there in the negative cases. And the model seems to be relying on that, by this highlighted region, relying on that to do the prediction. They also looked into another data set that was publicly available, and research has like been done on them. And they realized in many of the positive cases, when the patient were going the like CT process, like they moved their shoulders during the process, and that was part of the image. So the model instead instead of looking into the lung and finding the difference between like positive and negative cases, relied on this, which were mostly present in the positive cases. So they picked up this, and this is known as the shortcut because this is not related to the task itself. It's not related to looking into the lung, and that's why the performance of the model wasn't as best during the validation, during the like test time, and they weren't like applicable to be used in the clinic. So these are known as the shortcut, and as you can see, like the models these deep models tend to learn these feature more than the true feature that they have to look for. Another example is a very famous example of cow and camel. You've probably heard of that. This has been done a few years ago. Several researchers were trying to look into like the behavior of the model, especially for like a task or classification, wanted to see whether these models are actually as good as we like report the performance. So they wanted to tweak a little bit the data set and see if they're still performing well. And they realized when like they wanted to train, for example, a cow, learning what is the cow, what is the camel, and we have regular data set that we have, the model seems to be performing really well. But when we go to development and they changed like a few small things in the image, like the performance of model significantly dropped. Instead of like, for example, instead of this case to say this is the cow, it says it's camel. And in this case, instead of saying it's cow, it's a camel, it says it's cow. Why? Because like the model tend to learn background and rely on background to do the prediction than relying on the actual features of the cow or camel. So these are something that we realize that can hurt the generalizability of these of the models. And it's important to know the behavior of the model before using them. And right now, like researchers usually try to add these kinds of spurious feature or like shortcuts during the training to make the model see them and penalize the model for using this to do the prediction. The research is going on, and many people are actually working on this. It's a hot research topic right now. So now we know why these are important. So now I wanted to give you some malpractices that's done by us as a practitioner that hurts the generalizability of the model in machine learning and deep learning. So the malpractices can like be, the list can go on, but I'm gonna emphasize on some of the basic ones that we actually sometimes forget about their importance, and it can hurt generalizability. So the first thing is breaking the assumption of the independence, pre-processing or getting the statistic prior to do the splitting the data, relying on unrealistic metrics when we report the performance of the model, revisiting the test set, which is wrong. As I said, I'm gonna like, I emphasize on this because the test set is something that we have to see only once. And unfortunately, many researchers like make this mistake and they look into test set, but that is not test set, that's gonna be another validation set. So I will explain each of those a little bit more. So what I mean by breaking the assumption of independence, I mean that the training and the test example has to be independent from each other. We might know this like by heart and say, oh, okay, this is something that I already know. But in some cases, especially when we encounter low data set regimes, this is a common mistake by many practitioners. I give you like two examples of violations. The first one, assume that we have like a medical task and we have some, for each patient, we have like information like blood tests, CT scans. And for example, for each of those patients, we have to keep the information of that patient either in the training or in the test. We cannot divide this information on different slides of CT. We put it like some of them in the training, some of it in tests. So this is wrong. Another thing that we might miss is that when instead of training on the full images, we wanted to train on patches, like dividing these patches in separate sets. This is a wrong practice. We have to be aware of that, and we have to avoid. The other malpractice, as I mentioned, is the fact of doing some sort of pre-processing prior splitting of the data. For example, like feature selection, or like getting the statistic for the normalization, or the practices that we do to mitigate the impact of imbalanced data. They all has to be done here. So for example, when you're doing normalization, if you get the statistic on the full original set, it means that you visited the test set, and the statistic of the test set is present during the training. So this is a wrong practice, and we have to be careful about. Like, especially in the normalization, I've seen like many actually do this. So this is something that we have to be careful about. And as I said, the test set is there to be visited only once. And the other malpractice is related to the reporting metrics. Like it should be realistic because it can impact generalizability. For example, like, yes, accuracy is a good metric to like report the performance based on that, but is it enough? Like sometimes we rely on some feature and develop some models which are very irrelevant to the task that we want to do. I give you an example in medical that you sense how this can be important. So I will ask you, so I have a model that its accuracy is 99%. Is it a good model or not? So the thing is, we have to look back and see what is the task that we're talking about. What's the data set that we're talking about? Assume that we have like a problem of detecting cancer or non-cancer, and we have 1,000 samples. 990 samples are negative, 10 samples are positive. So if the model all the time says that it's non-cancerous, it's going to be 99% accuracy. So we cannot rely on this only metric in order to like develop model or like report the performance. This is not enough. We don't have to fool ourselves by these. So now we know about some of these pitfalls that has been done by us. And we also know about the impact of the importance of the generalizability itself, how important it is, because the overall goal is that when we develop a model, we wanted this to be able to perform as well on an unseen examples. And by doing those malpractices, we probably hurt the generalizability of the model. So now I would like to review a little bit about some of those like general practices that we as a practitioner have to know and do it in order to improve the generalizability or like decrease the chance of hurting the generalizability of the model. So, so just a recap about what we want. What we want is actually we're looking for an optimal model. We wanted to find a model that's not only have like a low training error, but also have a low test error, because the test error, as I said, and if you remember, it is a proxy for generalization error. It's not possible for us to provide a data set that include all the related examples to that particular task in the real world. That's why instead of having a generalizability, we rely on a test set, and we hope that the test set be representative of the real world or somehow. And we have to be careful about like cases when we have underfitting or we have overfitting. We don't want to have a model that has high biases or high variance. So there are some practices that help us to avoid these issues, avoid these situations, and help us to get to a better and more generalizable model. So we're gonna review some of this, and as I said, some of this you already know, but it's worth like mentioning. And if we mention like 100 times, sometimes we might even forget during the actual practice. So in the case of underfitting, we don't even have a good model on the training. So it's not even about the test set. It's still, we're in the training phase that we don't get a good performance. So there are different like practices that we can do in order to escape from underfitting situation and go to a place that we're close to the optimum. So one of the practices that we can do is that we can increase the model's capacity. What I mean is that maybe the model doesn't have enough capacity to learn the features of the data. So we go for a bigger model. We go for a like more deeper like neural network, something like that. Another practice is that reduce the constraint or regularization that we put on the model. Maybe we're putting so much regularization on the model. So by reducing that, we can give the model more freedom to explore and learn the features of the data. So when you're doing these practices to escape from the underfitting, you might realize that this is not performing as best, but that's why we sometimes suggest you train the model for a little bit longer. In this case, model can like learn through the mistakes it's make and help the model to have a better performance on the training and validation. So the practice for like underfitting is like, you can find other practices as well, but these are the main things that we can do usually to escape from this situation. In the case of, if we're not dealing with underfitting, we might deal with the cases then that we have like imbalanced data set. Imbalanced data set is very, very common in medical scenarios. In most of the cases, gathering like, for example, cancer patient is not as easy to find like those were healthy. So we have to be, when we have an imbalanced data set, we have to be careful about the metrics that we report, because those metrics gives us information about how the model performs. This is something that we have to do. And also in order to mitigate the impact of like these imbalanced situation of the data set and help the model to learn better, there are some like solution. One of the solution is undersampling. In the undersampling, we usually take the like majority class and decrease the number of samples here to make it to be more close to the like minority class. But you have to I have to mention this, that when you're using a deep model, like we usually want to provide more examples to the model. So I would not suggest to use undersampling when you have a deep model. We usually want to provide more examples. But another solution to handle a situation imbalance is actually the oversampling. In the case of oversampling, we take the minority class, try to create more sample in minority class and make it close to the majority class. So in this way, we mitigate the effect of imbalance. And that's how we probably will lower the test error and help the generalizability of the model. In the oversampling, there are different approaches that we can use, like generation approaches, like a SMOT or ANS or approaches so on, that's built on top of the SMOT and more recent approaches. most of these approaches actually rely on the neighboring information in the minority class. So for example, in that mode, they use the k-nearest neighbor, and they take k sample in each time they take k samples in the minority class, try to mix them and create a new sample. So in this way, they replicate a new example for the minority class. It's been there, I guess, in 2022, and many other works try to improve it for different scenarios. You can check for them. They seem to be very effective in some scenarios, but depends on where you're using. So I put this as a resource as well, so you can later go and check. So while we are at the imbalance scenarios, as I said, it's very common in medical, we also want to make sure that we're not making any mistake when we are splitting the data. As I said, when we have the original data, we want to split it in two sets, training and test set you're not going to see. But we have to make sure that when we are using, for example, a random split, we have to ask a question from ourselves: is this particular test set represent the true data distribution? Example, assume that we have two classes, negative and positive, and the number of positive examples is very limited. When we use a random sample, we ended up having a test set that is all negative cases. So we don't want this, because this test set is not resembling the data distribution. So what we are actually looking for is a test set that has a fair amount of information, data from each of the classes. So there are like some solution that we can use in order to make sure that the test set is close to the the true data distribution they have. So if you're using, for example, scikit-learn in order to split the data, there are some factors like stratify that you can turn it on. And use it as a way to make sure that you have a fair distribution on the test as well. So these are some practices that we usually do when we encounter imbalanced situation. There might be like more practices, but these are the most common things that we have to be careful about it or apply it. So aside from like imbalanced data set, there are some general practices to improve the performance of the model when we're dealing, for example, overfitting. So the thing is, like when we have a data set, we divide it in two sets, training and test. Then in order to find the hyperparameters of the model, because the model has parameters which we use, should be learned during the training, and it has hyperparameters that we usually find them during validation. So we divide it to training and validation. But the problem is that when we have like the data set is small, like a smaller sample we have, this is not a good practice, because the validations, the error in the validations that might fluctuate a lot depending on the validations, the set that is composed from. So what we usually suggest is that try to repeat this with different validation sets. So here is when we propose like cross-validation, or somehow a k-fold cross-validation. So instead of having the training and validation, we divide these sets, the whole training set, in two different folds. Each time, each of those folds acts as the one validation set. So in this way, we help the model to see different samples, different sets as a validation to find best hyperparameters. And when we find the best hyperparameters, it can help the model to have a lower test error and to be more generalizable. So these are the practices that we usually tend to do, especially when we have small data sets. And the cross-validation, actually we can have different version of cross-validation. You can study this a little bit more afterward. Like but just to mention, there are some cases, harsh cases, when we have like very, very small number of data that we can take each time, each sample to be the validation set in the training. Or in the case of like nested validation sets, we can go back, and here in this case, instead of having training and test set, we can have test set in different sets. And since in a nested cross-validation, we train the model, different models differently, and then evaluate it on different test set, we're like each model only sees the test set once, and we are not violating the revisiting test set. So another things that I mentioned was the metrics that we use. So there are other metrics that we can rely on. Instead of accuracy, we can rely on, for example, if we have like positive and negative cases, we can say how many positive cases, how many positive the model detected, like among all the positive, how many are actually truly been predicted, which is known as precision and recall. And these are very important metrics, especially when we're dealing with an imbalanced situation. Take this as an example, the same example that we had it before, like the model for like cancer, non-cancer, we have like 99% accuracy. Is it good? We have to look, like we have 990 negative example and 10 positive. The model predicted 999 negative and 1 positive. And the precision here is 100, but recall is 10. It means that the model is not performing well on the negative, which is the most important things that in that particular task. So these are the important things that we would like to make sure that we do. The other thing is that data augmentation is another practice we usually do. So as I mentioned in earlier slides, I showed you like how the model might encounter different like cases during the test, and that's part of the unseen example. And the model performance, if the model used to see very like high resolution images, it might and all in one shape, the performance might drop during the test. So what we would like to do, with this data augmentation, we would like to create that scenarios prior to testing. We want to create it during the training. So for example, we can like make the images blurry, crop the images, or add noise. So in this way, be showing like different transformation for the model and remove the biases of the model to only one particular like pose. And these are the practice that actually help the model, help us to create models that has lower test and improve the generalizability. So these are the practices, but I also wanted to talk about something which is known as distribution shift. This is not a malpractice per se that's done by us as a practitioner. This is something that can happen, very common in real world. And I wanted to draw your attention to the fact to different types of distribution shift and know about this shifts. Sometimes you try to do your best, but still you don't get a good performance. So you have to be aware there might be something else. So what is distribution shift? So assume that like we have the classification task, a supervised classification task. We have like the input and the labels, which forms like X and Y, and these X and Y actually create a joint distribution of P of X and Y over S, or like training, social training, they call it interchangeably. And the same thing actually applies to the test or target when we have like examples and labels, and they form like a joint distribution. So any kind of differences, between the joint distribution of the source or training and the joint distribution of the target or test is known as distribution shift. And distribution shift can have huge impact on the generalizability of the model. There are different types of distribution shift, but I will focus on two common types of distribution shift. The first one is known as covariate shift. Covariate shift is something that involves the changes in the input. So X is the factor that makes this joint distribution to be different from training and test. So take this as an example. Assume that they have a classification model, different classes, and for example, we have a class of bike in the training and validation, but when we go to the test, we have like, instead of images of the bike, we have like sketches of the bike or like painting of the bike. Yes, of course, all of them are bike, but the distribution of the input in the test is different from what we saw during the training. That can reduce the performance significantly and cause a huge, very low generalizability. So another types of distribution shift arises from label distribution shift. This is something, unfortunately, has been neglected by many researchers, and it didn't get enough attention as covariate shift. And it is something that arises from the why. So as an example, assume that we have two classes of red and blue, and these are the population of the red, this is the population of blue, but then we go from the source of training to the target or test, you realize that the population completely reversed. This actually can hurt the generalizability of the model significantly. And this can happen very much in the medical context when we're developing the model. So I just wanted to give you another source of like low generalizability situation and to know about these things. And about distribution shift, as an example, in medical context, again, assume that we have a study of multiple like hospital and institute that try to develop like an AI solution to predict like some types of disease. Like these hospitals, for example, like different types of people visit there, like different genders or like ethnicities used to go to one of the hospitals, and it's different from the rest of the hospitals. And the hospitals also like use different machines in order to do the like imaging, which is known as the vendor bias and can happen very often. Like, for example, all of them are trying to like get the images of their patients, CT images of the patient, but since they're using different machines, the distribution between the CT images from hospital A, B, and C might be different, totally different. This can hurt generalizability a lot. One of very famous example of this is the LIDC dataset. It's the CT dataset of lungs, and in that particular dataset, 4 different machines has been used, and you can see like the performance of them. If we build a model on one of them based on the information of one of those images, it's not going to perform as good on the other images that have been taken by other machines. So these are something that we have to know that might happen in the scenarios of medical imaging, and the approaches can be different. Sorry. The approaches can be different. First of all, this is a very hot topic research area. Many people are actually working on that. There are 2 different types of paths that you can take when you encounter distribution shift. The first is that you can go and try to detect distribution shift. You can use approaches like out of distribution detection, anomalies, or things like that. Or you can try to mitigate the distribution shift. You're already aware of the shift, and you're trying to mitigate this. You can use approaches like domain adaptation and provide a model not only working well on the training, but also working well when we have the shift. So in this way, I just wanted to give you some idea about what can like hurt generalizability, what we can do. Sometimes with small practices, we can avoid less generalizable model, but sometimes it's not something that we can do. Sometimes it's inherent in the model. Sometimes it's inherent in data that we gather. Sometimes it's like the shift is already there. We have to go and look for another approach. So that was the whole workshop. I put like some resources for you. I will add a few more resources later. And now we go to the coding part. So I will stop sharing this one and try to share the code, but just give me 1 minute because I have to run the code.
Sounds good. Thank you, Laya.
Thank you.
If there is any question, maybe you can put them on the chat.
Yes. So let me go and run the Jupyter. Try to. Okay.
So there is a question on the chat. Can we have the resources in the chat? So maybe if this is a Google Colab, Dr. Rafiee can share the link.
It's a Jupyter notebook on my personal computer.
So we're gonna share the resources after then.
Yes, exactly. I will share it. Give me 1 second. Okay. Can you see the code?
Yes, perfectly.
Okay, good. So I try to add like some information for you if you want to train it for yourself. So you have this information. So for today, I decided to create a synthetic data sets, an imbalanced synthetic data sets. And I wanted to run like SVM on that and show like what are the issues that we might have when we have imbalanced data set, what are the malpractices that we might do. And also I try to train a neural network on MNIST and show the underfitting and distribution shift. So these are the packages that we need. Like I mainly try to, even for the neural network, try to use the scikit-learn function. And so feel free to use them. These are the useful functions I thought that might be useful. So for this one, we wanted to plot the data. We assume that the data set I create is an imbalanced data set in a context of medical. This is to plot the data. This is also for the plotting the decision function. When we're using like support vector machine, we would like to see what's the boundary between the classes. So this might help us to have a better understanding of that. And this the printing function that I put and getting the errors. So let's first create like imbalanced data. This is something that I created. I will also share the data set that I created. You can play with it and see like how different things might impact the performance. Even like adding one sample in the minority class might be important in the performance. The place that the sample lies in also is important. So we load the data sets here, and we have the data set and the labels, and we can see, as you can see, like we have benign and malignant cases. The benign is in blue and the malignant in red, and you can see the number of reds is less than way less than the benign, and we are dealing with an imbalanced situation. So the first practice is to see the imbalanced data set and the wrong metric that we use. So in order to run a model, we like split the data set first and create like training and test set. But if you remember from the time that I mentioned about the imbalanced data set, when we are dealing with imbalanced data set, in order to make sure that the test set also includes the minority classes, we are using Stratify here in the scikit-learn, and we plot the data set, and we see that this is the training, this is the test distribution. We have limited number of the malignant case, but still we have some in the test. So what we want to do, we would like to develop a SVM model. In order to do that, we use the SVM from the scikit-learn. There are actually two versions of SVM, one for classification, one for regression. So that's why you see SVC here. So we can pass different kernels. Different kernels can have different impacts, but we are using polynomial here. We try to fit it on training data, and then we try to find the decision function here. So you can see that this is the decision based on the training data that we had. This is the decision function that model actually gave to us. So we wanted to do the prediction. For the prediction, we have a test, and the computer scores the accuracy of the model, and we realize the accuracy of the model is actually 84. And if we look into the decision function of the test, you can see the decision function is this, but the decision function is going to be the same as the training, but since the boundaries, the ranges actually change, you can see it here, not here. So there's no difference between them. So if you fix the range, you're going to see similar decision boundary, because decision boundary is not going to change during test. And you can see the performance is 84, but what does 84 means? We wanted to get the precision and recall. We get the precision and recall. We see the precision and recall is mostly good on the negative class, but it's not as good on the positive. So these are something that we have to care about. As I said, these are the wrong metrics that we use. Accuracy is not, I'm not going to say accuracy is wrong, but accuracy is not enough here. We need extra information about the models because we're dealing with an unbalanced situation. So the next task is incorrect pre-processing. So we can load the data sets. We use there are different versions of pre-processing that you can do. You can use either different functions from scikit-learn, or you can develop your own approach. So we are using standard scaling types of normalization. I pass the full data to it and get a transformation of that. Then we divide the data sets into splits of training and test, and then train the model. And then when you get the performance, we can see the performance on the precision on the negative class actually improved. So the problem is that we're not allowed to pass the full X, including the test set here. So this is revisiting the test set, because we are seeing something, we are getting the statistic from the test set in order to do the training. And this is wrong. So the correct practice is that we first, after we load the data set, we first have to create the splits. We have to create the training and test, and then do the pre-processing. And for the pre-processing, are only allowed to get the information from the training, not the full. And then do the transformation and train the model on the scaled or transformed training set. And we see that when we do this, the performance, the decision boundaries actually change. We're not sure if the pre-processing that we were doing is correct or not. The point is that we shouldn't do the pre-processing on the full test. We shouldn't get the statistic of the test set prior to splitting. And when we get on the test data, we can see, oh, okay, this is the performance of the model is not improving that much. Maybe the pre-processing is not as good as it's supposed to be. But the practice here is that no matter what you get as the result, whether you get a better result or not, the correct practice that you have to use only the training statistics, not the test. The next thing is actually involved in training with the imbalanced data set and how to mitigate it. As I said, one approach is undersampling, another approach is upsampling. We usually don't do, I don't suggest undersampling. I usually do upsampling. So in order to do that, so we might have different approaches. First, after we load the data, we split the data, and then we do the the task that we have to do for the mitigation of the imbalance situation. One way is that it actually lies intrinsic, it's actually related to the function that we are using. For example, in the class of SVM, in a scikit-learn, you already have something that can help the model to learn better. By setting the class weight to be balanced, you are kind of forcing the model to, during the training, to penalize the positive cases, which has been negatively assigned as negative, more than like negative case itself. So this is, in this way, we're trying to put like more weight on the negative cases, because we have, positive cases, because we have less number of positive samples. And then when we try to predict the examples, we can see the performance actually improved, not only on the malignant, on the benign, but also malignant cases. And this is something we actually need to do when we want to do the, when we want to train on the imbalanced data set. Another way is that we can use different oversampling, or random oversampling, or a smooth. I'm gonna see you smooth, how we're gonna do this. So after splitting, we're gonna define the sampling strategy. I suggest you all go over and see different versions of F-mode. And if you go here, you can see like there are different approaches that you can set in order to create the samples. And we set it as to be automatically. So it's grab all the information from the training and try to try to propose something that the model thinks is the best, the smooth, I mean. Then we'll do the training, plot the training data. As you can see, the number of minority classes improved, but there is something that we have to be careful about. Most of the sample are actually put it here. There might be something, this might also impact the performance of model. Maybe one wants to have a more spread and more variance in the like the samples that we created. So when we compare the performance of on the stop training. When we train the model on the training set using these new data sets, when we see like a more balanced situation and we have more minority class as well, we can see the boundary actually changed a little bit. And when we run the prediction on the test, we can see the performance actually went a little bit higher. Still is not as high as the suggested approach by scikit-learn, but these are something that we can play with it in order to see what's best for the model. But you have to remember, you cannot take the test set and see if it's not good and go back to that. You have to split even a small subset as the validation and do the like comparison on the validation, and then go back and retrain the model. So now I would like to draw your attention to the K-fold cross-validation to estimate the whole lot performance. As I said, in the cross-validation setting, we have when we have like a smaller number of sets, in order to find the best hyperparameter for the model, we rely on the validation. But since the validation is small and might not be a good set, we try to like go over different sets, and each time takes one of the sets as the validation and see if the model is performing well. So in this scenario, instead of like having scikit-learn, instead of having like SVM, I decided to look into the decision tree, and I trained the decision tree and compare the performance on 5 different folds. And as you can see, when we have a 5-fold cross-validation, the performance is actually higher. So these are the practices that we would like to do when we have like limited number of samples. The other example is actually low capacities and distribution shift. I first go over low capacity. In the low capacity scenario, like I wanted to also look into another data set, which is like the data set that I created, something like there might be some issues with the data set. I just wanted to show you what's the impact of imbalanced data set. But now we have a more standard data set of MNIST, and I can share these as well with you. You can either use the PyTorch libraries to load the data set, or you can use this information I put here in order to load the data set. So we have the training, we have the validation sets, and we try to create a like neural network in order to do the classification with these tasks. And we take the standard, like very basic and a standard neural network from the scikit-learn family, and we didn't change anything. We just tried to train the model for 5 different networks to realize, oh, okay, the training error is low, so we're happy now. But we want to also to check what are the performance of the model, what's the performance of the model overall on the validation set as well. So we realized the validation accuracy and also training accuracy is not that good. It's around 11%. So this gives us something about the low capacity of the model. Maybe the model is not trained enough. Maybe there's something about the model that we can add to improve the performance of the model. One thing is that we can, like, instead of having, like, for example, the 10 neurons in each layer, we can like pass 100 instead of like 5 epochs. We can train it like for 10 epochs. In this way, probably we help the model to explore more the data, and maybe the performance get higher. So we can see like the performance, the loss is like around 4, but when we go, sorry, when we go to the evaluate the accuracy of the model, the training and the validation accuracy. Right now we're learning our accuracy. We can report other metrics as well. We realize that the performance goes as high as 89. So this is done on the validation again. So in this case, we know that from the previous experiment on validation, we realize that the model doesn't have enough capacity to explore, to like learn all the features of the data. It doesn't have enough parameters. So we provide more parameters for the model, make it a little bit bigger, train it a little bit longer, and now we have a better performance here. In another example, if you wanted to see, just to give you an idea about the effect of distribution shift. So again, below the data, in order to create a distribution shift, I just have to say this is a very naive example of distribution shift. Distribution shift can be very different. For example, in the case of MNIST, MNIST are like grayscale images of digits from 0 to 9, right? But we have a color dimness as well. It's exactly the same as MNIST. Like the shape of images, everything is exactly the same, but images of color instead of gray image. And if you train a model on regular MNIST and grayscale and go for the color dimness, the performance will drop significantly. Those are the type of one of the type of distribution shift that might happen. We have like another data set similar to MNIST called USPS. It's exactly the same number of digits, but the shape of the digit and the background is a little bit different, and you can see the model's performance actually drops when you use the model that's trained on MNIST to be tested on USPS. But in this case, in order to create a distribution shift, I decided to add a little bit of Gaussian noise. So I took like half of the example and added a Gaussian noise using SkyImage libraries. You can use whatever you want. You can play with this. But once we created those, we try to like train the same model as before. That here we had the highest performing model to work on this. So again, we have 10 different training on 10 different iteration and longer number of hidden neurons. And we observed that the losses is almost similar, but when we try to report the training and validation accuracy, the accuracy on the test, which has the corrupted images, actually drops like more than 10%, 15%, I guess. The one that we had was 89, but here what we have is 72. So now you can see how distribution shift can impact the performance of the model. So we're not going to talk about like how to improve this, but I just wanted to give you some idea about how these models can perform under different situations. So that was the like full the coding practice. I hope that it was helpful, and I can, I guess if you have any question, I'm happy to answer.
Thank you so much, Dr. Rafiee. That was super interesting, very well done. I think the examples you showed in the notebook are perfectly correlated to the presentation, and you explained a lot of very interesting things. So thank you so much for sharing all of this with us. So now it's time for questions. So feel free to either unmute to ask your question directly, or put them on the chat, or raise your hand. Please don't hesitate. So I don't see any questions on the chat for now. So maybe I can start with a question of mine. So I think you mentioned that the pre-processing should be done on the training and not like the whole set with the test set.
Yes.
In the case of deep learning, where we have a validation set, how does that work? Should we pre-process on the train plus validation set, or only the train, since the validation serves as a test set, kind of?
Oh, if validation set serves as the test set, you cannot look into the test set. This is like forbidden. Like, as I said, like the test set should be only seen once, and this is one last experiment that you run, and only once.
Okay, I see. Great. So we should normalize only, for example, on the train.
Normalization, for example, normalization, during the normalization process, what you do is that you get the statistic from the training, then you transform the training. You also transform the test, but with the statistic that you get from the training, not the statistic of the whole data set. This is something that we have to be like careful about it.
Yeah. Actually, it makes a lot of sense, because if you have like only one image on the test set, you cannot just take its own statistics and normalize it.
Exactly.
Thank you very much. And do you have, I don't see any questions on the chat. Was
it obvious, or like too easy or too hard? I don't know. Like, no, I hope that it's helpful.
Oh, I see the first question. So there is a lot of thank you on the chat, actually. So thank you so much. So the first question is, how can we spread the samples in upsampling?
What do you mean by spread?
I think it means how do you increase the number of samples when you do upsampling?
Oh, as I said, like there are various approaches that you can do. One of them was with mode. The other one is just not increase the number of samples by like penalizing like the minority class. So this is another practice that you don't create like new samples, but you put more weights on the minority class, and because you don't want to have mistakes on the minority. In terms of like upsampling, mostly we generate, and mostly we rely on the neighborhood information. Whether you're using a mode or any approaches, most of them try to take the information from the minority set itself. Sometimes, for example, in the example that I showed here, I relied on the default scenarios. We take like 5 examples from the minority, combine the information of those. You can go back and read it in Smooth how we do it, and then create a new sample. Maybe if you get more sample, you have better results. These are something that I put it here for you to explore. And yeah.
Thank you so much. I think there is a very related question as a follow-up. Is there any way to use upsampling / downsampling / SMOTE for image datasets? Like,
So
do the libraries you showed on this notebook work on like other kind of data?
yeah, I guess similar approaches are gonna be will be able to be applied, because the background and the way these algorithms actually work is just using k-nearest neighbor. You can apply k-nearest neighbor on images as well. So you can use the information from these approaches to be able to apply on the images as well.
Thank you so much.
But yeah, but I just have to mention there are, like, I put some resources for these recent approaches, but I've been checking and I see there were several other papers that try to improve the performance of, for example, smooth, and you can look up for them. Some of them are very seems to be very working very well. Actually, I saw it on images as well, so you can check for that. I put the resources and you can find them there as well.
It actually makes me think, because these approaches are really recent, right? If this is 2022, how,
exactly,
like in your field, which is like a very hot research topic, how do you stay up to date with like the new libraries, the new tools you can use to avoid all of these generalizability problems?
So in terms of like, this is a very like general question. What do you usually do? So I'm not going to say that I'm as updated as I supposed to be, but the thing is, most of the time when you're in real world, in the case of mine, when I'm dealing with medical images, in the, like, not images, like medical information, sometimes it's not as clean as it's supposed to be, like benchmarks like MNIST. So I mostly get into the situation that the performance of the model is not even good on the training. So I have to look for like things to improve the performance on the training and also on the validation rather than the test set. So that's how I try to Google and find new things, new libraries. But scikit-learn also have, like, I'm not using scikit-learn that much, mostly PyTorch, but like in the scikit-learn community, like people are very active to answer the question or provide the solution for like your problems. So yeah, look up online and there are a lot of resources that you can find. It's not easy to stay up to date. It's because the amount of like papers and new approaches that comes in are quite a lot, and the area that you work sometimes doesn't need all of those information. So I tried not to go from branches to branches, but some of those things which are general, like cross-validation and stuff like that, are good to know. Whatever research field you are in, like medical, non-medical, NLP, whatever, it's good to know about those terminologies and the frameworks and libraries.
Well, thank you so much, Dr. Rafiee, for your time and answering the questions. I don't see any more questions in the chat. So for the participants, I want to let you know that there will be a tutorial where you can ask questions if some come to your mind next Friday at 1 p.m. So I would like to thank Dr. Rafiee very much for her time and sharing all of her knowledge here today with us.
Thank you for inviting.
Yeah, our pleasure. And yeah, have all a great Sunday, and we will see all of you at the closing ceremony and the tutorial. Yeah.
By the way, should I share like, where should I share like this information, the code as well, right?
Yeah, if you can make it a Google Colab, and then we can make it available to the participants.
Okay, yeah, I will do. Okay.
Great.
Thank you.
Thank you so much. And there is a question, where is the closing ceremony? So the closing ceremony will be held remotely on Zoom next Saturday. So same time as the usual seminars, 10:30 a.m. Montreal time. Okay, so thank you so much for your time again, Laya, and have all a great Sunday. Thank you very much.
Thank you. Bye.